Right. So this is Griffiths, right? So it's a introduction to electrodynamics. Uh, yeah, I know this is maybe just a bit too advanced for me because I haven't done anything for 1 month. Right. This, yeah, might not be the best choice, but we should start, right? We should start with something. So let's just do it. Okay. So first let's see the contents. I know it's like this is lagging a bit, but whatever. Okay, these are the contents. Cool. Right, so first we got vector analysis, which has the first chapter is just vector algebra. So it has vector operations, right, vector algebra component form, triple products, okay, position, displacement, separation vectors, how vectors transform. So all of this part, I mean, this is pretty easy, right, because this was, yeah, part of the syllabus that I went through. Right. So I mean, this is not something I would like to do. Instead, I'll just go to the second section, which is differential calculus. So first you got ordinary derivatives, then the gradient, then operator del, then the divergence, curl, product rules, second derivative, then you got integral calculus. Fine. So I think we should start from the second chapter. So first you just got like a bunch of math topics, and then there are these things, electrostatics, and then you get to other stuff. Fine. So just start off at the second chapter. Okay, why is this taking so long to load? Suppose you got a preface. I won't be reading any of this. Yeah, whatever. We don't care. Honestly, I don't. I don't care about the introduction part really. So first is like electric charge units. Oh, this might be important. The subject of electrodynamics is plagued by competing system of units, which sometimes render it difficult for physicists to communicate with one another. The problem is far worse than in mechanics, where Neanderthals, okay, still speak of pounds and feet. For in mechanics, at least all equations look the same, regardless of the units used to measure quantities. Newton's second law remains F equal to ma, whether it is feet, pounds, second, kilogram, meter, seconds, or whatever. But this is not so in electromagnetism, where Coulomb's law may appear variously as, okay, so this is Q1, Q2 upon R squared, R hat in a Gaussian unit system. So, okay, this is like the force, the Coulomb's force. Um, okay, so this is weird. Right, I'll be dealing with SI all the way because I don't want to be dealing with these not so popular unit systems. I'll just be dealing with SI. So yeah, 1 upon 4 pi epsilon naught, and then Q1 Q2 upon R upon R squared. And yeah, that should be good enough, right? Of these systems in common use, the two most popular are Gaussian, which is CGS. Okay, so it's centimeter gram seconds. Wait, why? Why is this different, and how did this happen? Where did this factor go? I mean, it should be there. It's like 9 times 10 power 9. What about that? So how does that factor just go away? That doesn't actually make any sense, right? No, it doesn't. Because you got Gaussian, which is, so they're saying it's CGS system. I doubt that's the case because this is, yeah, I mean, like it's exactly 1 over here. This complete constant that just became 1, which does not make sense because how can that happen if you are only dealing with powers of 10, right? Centimeter, 10 power negative 2 meters, grams, 10 power negative 3 kgs, and seconds is second. So how does that factor of 9 get cancelled? There must be something more. There must be something more than just the CGS system. Okay, okay, then you got SI, which is MKS. Oh, okay, meter, kilogram, seconds. Fine. Then elementary particle theories favor yet a third system, Heaviside Lorentz. Although Gaussian units offer distinct theoretical advantage, most undergraduate instructors seem to prefer SI. I suppose because they incorporate the familiar household units, volts, amperes, and watts. In this book, therefore, I have used SI. Thank God I don't have to learn a whole new unit system. Appendix C provides a dictionary for converting the main. Okay, that's nice. I don't think we'll be using that if they're already in SI units. Why is this blank page left here? Okay, so now we start off for real now. Chapter 1, Vector Analysis. Oh, wait, no, I think this is something we should skip. So what do you have? Just got, right, so it's just introduction to vectors first of all. Addition of two vectors, easy. Multiplication by a scalar, easy as well. Dot product of two vectors, no big deal. You got cross product. What else do you have? What is this? Let C be equal to A minus B and okay, and calculate a dot product of C with itself. So I mean, just like A square minus 2A dot B plus B squared. Why do you ask that? I mean, yeah, so instead of writing AB cosine theta, where you don't know what theta actually is, you will have to explain them what theta is. I'm just gonna write A dot B, right? Yeah. So yes, this is actually the law of cosines, because that's from where this actually is. Yeah. Hey, actually, that's a nice thing. Like, think about it. Just using a dot product, you can kind of like prove law of cosines. That's weird. Wait, let me just think about it. I know it's not a math course that we are doing, but still, just think about it. So, say you got a seed. Okay, this is not what I want. I think this will be no, still bigger. 29. Yeah, this is the thing that I want. Cool. So let's just say you have a triangle like this. So you have like two vectors, A vector, B vector. It should be going from here to here. This is going from there to here. You got C vector, which is the sum of these guys. Say you have the angle theta, right? So this angle theta, and or okay, you know what? Since they are using that angle to be theta, I'm gonna use that as well. Uh, okay, maybe there's some other way that you can do this. Maybe. Oh, let's do it like this. So we'll just say that, right? So this is a vector, right? Because I want to match with what they are doing. So just a vector over here and then b vector over here, right? And you got c vector. So of course c vector is just a vector minus b vector. Then you want to figure out what's this length given these two lengths. So you know what the magnitudes of a vector and b vector is, a and b, right? You know those values. And let's say you also know this angle theta. Then you want to figure out this guy. So instead of doing all of the trigonometry and actually establishing law of cosines, you can just cheat a bit. I don't want to call this cheating, but it is somewhat like that. Okay, so what we'll do is we'll just figure out the magnitude of this guy, right? How do you do that? You just do square root of c squared. So c is the magnitude of this thing. But then the way to do that is like, so how we will do it is actually like square root of c dot c. So c vector dot c vector, because since it's like in the same direction, the angle between these two vectors, c vector and c vector, is just 0. So like cosine 0 is just 1. So yeah, I mean, this just gives us c squared, and square root of that, that's just c, right? So that's the thing we are dealing with. But then remember what c vector actually was. It was just square root of a vector minus b vector, and then you got this thing, a vector minus b vector once again. So dot, of course, it's a dot product. Then applying distributivity and all that stuff, you can write like this: a squared plus b squared minus 2a vector dot b vector, right? Or you can alternatively write this whole equation like c squared is equal to a squared plus b squared minus the thing. And I guess we should be using small a and small b, but like whatever, doesn't really matter. So we'll just make these capital A and capital B and capital C instead. I know you usually use that for angles, but fine. So what you basically get is like c squared equal to a squared plus b squared minus 2a dot b. Now, if we have already established that a dot b is equal to ab cosine theta, then yeah, this basically proves law of cosines. But right, for that you should have to prove that a dot b is, wait, how do you even define a dot b? We are not getting into all that maths and definitions. Should we? No, we already know this, right? Okay, so I think it depends on how you define a dot b. You could just define it like ab cosine theta, right? Who cares? Just define like that. Yeah, like okay, for a cross product, you can define it like the area of parallelogram, so AB sine theta, that makes sense. But then this has no geometric meaning. So this is, yeah, that is the definition, just AB cosine theta, huh? Interesting. Well, whatever. This is the law of cosine. Or you could define like that, yeah, just, decompose the vector in our three coordinates system and then, take the dot product like the way you do. So for example, you got this 1, 2, 3, and then that dotted with 2, 3, 1. The way you do that is just, this times that just 2, and then this time that's like plus 6 and plus 3, something like that, right? So 11. Yeah, you could define it like that. Two different definitions, and then you just have to prove that this definition is pretty much the same thing as this definition. And there you go, you got law of cosines. Yep, easy as that now. And this is actually a better definition because now you can, explain why distributive works, right? And why it's commutative and all that stuff. Because it's just multiplication, pairwise multiplication. Doesn't matter if this was on the left or right. It would still be the same thing. So A vector dot B vector is the same thing as B vector dot A vector. Yeah, because, the formula is just symmetric. No big deal. We already know all of this. But it's actually nice. It's like a proof of law of cosines. Fine. Then you got cross product of two vectors. Yeah, everybody knows what that is. Oh, I think they also have. No, it's just distributive. Fine. Right. Everybody knows this. Geometric is the area of parallelogram. Yeah. So what you have, using the definitions in equations 1.1 and 1.4 and appropriate diagrams, show that the dot product and cross product are distributive. Oh, right. So like this actually, I think I proved somewhere that cross product is distributive, and now I don't remember what method I went with. Okay. So once again, what's the definition in equation 1.1 though? Where is it? Huh? Where's 1.1? Oh, okay. This is example 1.1. I don't see what equation you are referring to. So these are equations. Okay, 1.5, 1.4, 1.3, 1.2. Then there must be 1.1 somewhere here. Right. So dot product of two vectors. That's basically this thing, AB cosine theta, where theta is the angle. Right. Yes. So that's the definition of dot product. But what about the cross product? Oh, and 1.4. So where's 1.4 by the way? Right, so it's just AB sine theta n hat, where n hat is perpendicular to both A and B and given by the right hand rule, and you know the thing. Right, so using this, we have to prove it's like distributive. Okay, this is weird. Fine. So now, yeah, well, first what we'll actually have to prove is, the way we actually calculate dot product, right? Why do we do it like that? Just, pairwise multiplication and then addition. So why is that the dot product really? Okay, how do I even approach this? Without proving that it's distributive, you can't actually just, prove that actually. So, we will first actually have to prove that it's distributive geometrically, and then you will be able to do everything. Right, okay. So, geometrically, right? We can't do algebra right now. We just have to use geometry. So fine, like let's just prove that a vector dot b vector plus c vector is equal to a vector dot b vector plus a vector dot c vector, right? Yeah. Okay, cool. So just consider some vector, which is a vector, and then you have b vector and c vector. They might even have a plane or something. That's weird. Okay, I think we should just, first of all, figure out b vector and all that stuff. Okay, so this is b vector, this thing is c vector, and this thing is b vector plus c vector. Okay, so basically what you have to do is like a vector dotted with this thing. Okay, well, since we don't know that it's distributive, you can't take a vector as, something perpendicular to this plane and something that's on this plane. You can't do that, unfortunately. Oh, oh god, then how am I supposed to do this? But still, like, okay, a vector has some angle. No, it's not going to work. Like, without algebra, how can I even, how do I even prove this from geometry? I think there might be proof of this, but then just how? So for a 2D case, it's very easy to prove, but then for a 3D case, this becomes complicated, doesn't it? Okay, think. Uh, how am I supposed to prove this that, it is what it is? It is distributive. You can't split a vector into two components. You can't. So then what do I do? Okay, it's like the component of a vector in the plane, right? Doesn't matter what angle this is making with it because yeah, right. The projection of a vector onto the plane. You'll be dealing with that in any case, right? Without without having distributivity, this is hard. This is really hard to do, I think. Okay, I think. There must be something that I can do. Uh, we know it's just the projection of this on that. Ah, okay. Think there must be better meaning for this. Okay, let's think of a plane. So let's think of the plane which is perpendicular to a vector, and then think about any random vector. Like, okay, this is the origin, and then you think of any random vector. So then the dot product is basically just, you just resolve this as a vector on the plane and a vector along a vector, and then you just multiply this length and that length, right? Okay, so now let's think about two vectors and see what happens. So, right, if you got two vectors, I think you need to imagine it in 3D. So like these are going inside the plane or something. Anyway, what's going to happen is that you can break both of these and then, right. Um, so let's just say that this is our B vector and C vector, and we'll just say that B vector is equal to B star vector and B naught vector, and this will be C star vector and C naught vector. Okay, where C naught vector and B naught vector are the components on the plane, and this is the perpendicular component. All right, and I guess geometry basically guarantees that you can only find like this. This is the only way this is going to be split up, right? Sure, there can't be a different way. No, there can't be. Okay, so then of course B vector plus C vector, that's actually the sum of all of these four vectors, right? So when we say A vector dot the sum, what actually we mean is like A vector dotted with C star vector plus B star vector plus this vector C naught vector plus B naught vector, right? Okay, but now think about it. This vector has this as the component that is perpendicular to the plane, and this is just some vector that is in the plane. So it's the component that is along the plane, right? So then, of course, by definition, right, the way we are actually defining it, or using like AB cosine theta stuff, because clearly, a dot some x vector, that's like saying a length of a multiplied by the length of the component of x along a vector, right? Yes. So using that definition, I know that's not quite the definition they are using, but I think this is a better definition anyway. It's basically the same. It's the same because a b cosine theta, that is the thing, right? So b cosine theta, that just takes a component of b in yeah, which is along a vector, right? So then this thing by definition is just a times the magnitude of this c star vector plus b star vector. Of course, this has like sign and everything, so I can't just make this c star plus b star, because what if c star is actually negative, right? So it's not along along a vector or something like that. Okay, cool. I think you can make a signed magnitude. Does that actually make sense? No, it doesn't. But yeah, I guess it's okay. I mean, since you know what I'm talking about, I can actually get rid of all of this. It's just like that. Right. Once again, if it is along a vector, it's in the direction. If it's pointing to its positive, it's opposite, it's negative. And there are no unit vectors over here. The sign is the thing that indicates direction in this case, right? Okay. And of course, now these are just numbers basically, right? So a times c star plus b star, that's what this quantity will be. But then a vector dot b vector, was A times C star anyway, and this was A times B star anyway. And since now we're not dealing with vectors, we're just dealing with numbers, right? Yes, A times C star and then plus A times B star, that is actually just equal to this thing. So there we go, we just prove that dot product is distributive. And from that, you can just get the formula directly, right? The formula for dot product. Yeah, yeah, much. Right, so that's awesome. Okay, cool. Uh, so now we just prove that dot product is distributive. And we also have to prove that the cross product is also distributive. So this might be more complicated though. Fine. Right. Let's think about it. So once again, you got A vector. You still got the same setup. You have this plane, you have B vector and C vector somewhere in this 3D space. You are going to write them as B star plus B naught. Okay. This is B star. So this is B star and this thing is B naught. And this will similarly be just C star and C naught. Right. So one thing we could do is actually prove that A vector cross X vector is just the same thing as A vector crossed with X star vector, right? Yes. Well, once again, it's gonna, I think, require distributivity or something. I don't think that's correct. But no, it doesn't require distributivity because what it says is that, you know, A vector dot B vector, sorry, cross with B vector is just A times B times sine theta that times n hat vector. So of course, if you have two random vectors, A vector and X vector, or let's just say B vector, and then you have this in some plane, right? They must lie in some plane. It can't be that they are like, right? So they must lie in some plane, and then you can actually decompose this B vector like this. You can say it's B naught vector like this, and then, you know, B star vector like that. Okay, this is of course a plane, and now you got n hat vector. So using the right hand rule, right, it should point downward, of course. Both for A vector cross B vector or for A vector cross B star vector, right? In both cases, this should actually point downwards. And you can do this for any kind of angle between A vector and B vector. It's no big deal, right? Yeah, all that matters is that we just go from A vector to B vector, right? Exactly. And your and angle between them is of course just, you know, what was I going to say? Oh yeah, okay. The angle should be less than 180 degrees, more than 0, right? And then you can do this. Just go from A vector to B vector, apply the right hand rule. There you go. You got your n hat direction. Yes. And the same thing will be for A vector to B star vector, right? And then if this angle is actually not less than 180 degrees, like more than that, then you just take this angle instead and then do the same kind of thing, and now n hat is going up. So yeah, two cases I'll be dealing with one case only, right? So this is basically point downward. Fine. Then what we just did is right, so since we are dealing with AB sine theta, well, B sine theta is just B star, right? Yeah, I mean, of course, it's just that, like, okay, this angle is our theta, right? So then this thing that will be 90 plus theta or 90 minus theta or something like that, or just say, you know, use this one. So just, this is just pi minus theta, right? And what is it going to do once again? Right, our B star. Oh god, what was I going to do? Oh yeah, so the sine of this angle, sine of theta, is the same thing as sine of pi minus theta. So then you can just do sine of pi minus theta times B. Well, that is just this length, right? And that length is the same thing as that length, parallelograms. So what you basically get is like B star is in fact equal to just B sine theta in all kind of cases, which means what we really want is just this vector's length times this vector's length, right? And then sine theta, the angle between them is 90 degree anyway. So yeah, just one, and then this, right? So what we just proved is that A vector cross B vector is the same thing as A vector cross B star vector. So you can just get rid of these B naught, C naught things. We don't really want them, no. Like proving that A vector cross B vector plus C vector equal to A vector cross B vector plus A vector cross C vector. That's the same thing as proving A vector cross B star vector plus C star. Okay, this should be star on the top. Doesn't matter, just notation, right? So B star vector plus C star vector, that's equal to A vector cross B star vector plus A vector cross C star vector. That's basically what you want to prove, right? Exactly. And also when you add these two up, you can do the same. It's the same story. Like P naught vector plus C naught vector is the component that's along the plane, and then the addition of these two vectors is the one that is perpendicular to the plane, right? Okay, so then the left hand side, which is A vector cross B vector plus C vector, is just A vector cross with the sum of these two vectors, right? Which is just oh, and by the way, like, oh shit, I don't think we should have done that. Yeah, we should definitely not have done that. Oh, this is not. Oh god. No, not the star. We should be leaving with the dot. Okay, sorry for this. Look, here what we did was that we decomposed this, and then we just took the vector that is perpendicular to a vector to be b naught. Oh, that's b naught vector, isn't it? This length we're talking about is not b star, it's actually b naught. So fine. Okay, a vector cross b vector is just a vector cross b naught vector. No big deal. It's the same. You can get rid of these two now in that case. So what that means is just, the left hand side, a vector cross b vector plus c vector is the same thing as a vector cross, well, b vector plus c vector has the sum of these two as the perpendicular component, which does not matter. And then have these two sum, that's the component parallel to the plane. So basically the left hand side is just a vector cross b naught vector plus c naught vector. Right. And now what we have to prove is that it's distributive for two vectors which are on the plane perpendicular to a vector. Which, how I'm supposed to be doing this, I have no idea. Well, the n hat. I think at this point, you can think of it like complex numbers, right? So yeah, this is a weird idea, but I think I've done this once or twice. So what I'm thinking is our b naught vector and c naught vectors are complex numbers in this plane, right? And when you cross that with this a naught a vector, sorry, which is perpendicular to the plane, what you're actually doing is you are rotating this thing 90 degree, right? Yeah, it's 90 degree in such a way that when you use the right hand rule, right? Let's just do it like this. Raise your right hand, put your thumb along a vector, put your fingers along p naught vector, and then curl your fingers. So that's giving us the direction in which you have to rotate this, right? So you just rotate by 90 degrees and then you land over here. So taking a cross product, so a cross this thing, it's basically just rotating this by 90 degrees. So if you can think of these as complex numbers, then a vector cross b naught vector plus c naught vector, or any vector in fact for that matter, any vector that is in this plane perpendicular a vector plane, right? Well, this is the same thing as, okay, think of x vector as a complex number for now. Fine. So this is just what is the magnitude of a, of course, well, that times iota. This is not I hat. Okay, this is not the unit vector along x-axis. This is iota. I think you need to understand what I'm doing. Well, whatever. This is iota and that times x vector. So this, yeah, I'm thinking of x vector as a complex number, and then iota times this thing, but that is rotating by 90 degree, and then this is times the magnitude of a, which I'm just calling small a, right? This is not a complex number, it's just a real number, whatever. So basically, like a vector cross with b naught vector plus c naught vector, isn't that just a and that times of I times b naught vector plus c naught vector? But then it's just multiplication of complex numbers, which is distributive. So you can actually write like this thing, a times, or instead, ai p naught, because this is a scalar anyway, right? It's just a number in this case. So yeah, a b naught vector and plus a iota c naught vector. And with that, we just prove that for two vectors which are in this plane, you can just use distributivity. So like a vector cross b naught vector plus c naught vector, that's equal to a vector cross b naught vector this part plus a vector cross c naught vector. And in that way, we just prove that cross product is actually distributive. And from that, you can get the formula for cross product. So that's awesome. It's a good thing I actually learned complex numbers. Because otherwise this would be hard to prove, right? Anyway, next you got vector algebra, component form. Okay, whatever. Right. Everybody knows that. To add vectors, add like components. Come on, are you serious? Yeah, I know that. I mean, this would be awesome if they actually, gave geometrical proofs for these properties. Hey, there's more stuff as well. Okay, so we also should be doing this. When three vectors are coplanar. Oh God. Oh, so we actually had to do it in two parts. So first you just have to show that it's distributive when the three vectors are coplanar, and then in the general case. We did the general case directly. So we don't have to do the first one in that case because we already proved it for all cases. Then problem 1.2 is the cross product associative. So spoiler alert, it's not. Right, it's not. Okay, if so, prove it. If not, provide a counter example. Let's give it a counter example. Let's think of this. I hat. So now this is the, or I instead let's use x hat instead because that's what they are using as well. So x hat crossed with x hat once again. This is not going good. I don't like how there's a bunch of x. Okay, I'm gonna use I hat instead. I hat cross I hat, right? That's our A and B, and that cross with C vector, which will say is like J hat. Okay, is that equal to I hat crossed with I hat crossed with J hat? Should be cross over here. So this is just zero. So zero vector crossed with J hat, zero as well. And this I hat cross J hat is just K hat. I hat cross K hat is negative J hat. So negative J hat is not equal to zero, which means this is not going to be working. So we provided a counter example. Next. Okay, we already know all of this. Wait, I thought we would not be doing this. We are still doing this now. Whatever. Fine. Write the formula. Yeah. We don't need that. So instead of writing it like that, that determinant, yeah, you can just write it like this. So ax, ay, az, that crossed with bx, by bz. I'm gonna show you a method that doesn't involve writing all of this. So what you do is for the first row, forget about the first row and think of the second and third row and do this thing, this and that. So this in plus and this in minus. So let me give an example. Let's say 1, 2, 3 and cross with 3, 2, 1. Yeah. So this is going to be like, first you just forget about the first row, you do this thing, this determinant, 2 by 2 determinant. I think that's not a big deal. Just 2 times 1 is just 2, that minus 6. Alright, then once again forget second row, do the other two rows, but this time what you have to do is actually write down the first row below this. So 1 and 3, and now do this determinant, right? This 2 by 2 determinant. So 3 times 3 is just 9, minus 1 times 1 is just 1. All right, then forget about third row and do this determinant. Okay, which would just be 2 minus 6, and there you go, you get the cross product, which is just negative 4, 8, negative 4 once again, whatever. So yeah, that's better way of doing cross products. Of course, you don't have to write all of this, and honestly this doesn't like look intuitive to me. Why should you have unit vectors inside a determinant when a determinant is basically what's used for numbers, right? I know you can generalize to many other weird things, complex numbers and whatnot, but still, why would you want to generalize to vectors if you can just use this for real numbers all the time? So I would say don't do this. It's just a waste of time writing all of this down. No, don't do this. Okay, Example 1.2. Find the angles between the face diagonals of a cube. What? Angle between the face diagonals of this cube. So this, and that. Okay, cool. Well, of course, this is the 0, 0, 0 thing. You have x. Why is this coordinate system so bad looking? This is 1, comma, this is 0, comma, 1, 0, 0. Okay, whatever. Well, this would in that case be 1, 0, 1. So 1, 0, 1. That's this vector, and we also want this vector, which would be um right. So it's just 0, 1, 1. Okay. So the dot product between them, that's just equal to the length of this vector times the length of that vector, which is square root of 2 times square root of 2. And this is not a dot product, it's just scalars, just multiplication. That times the cosine of the angle between them. So that's exactly what you want to find. Cosine theta. Once you find it, you can find theta. Right. So this is of course just, well, this doesn't matter. This doesn't matter. Just 1. So yeah, 1 upon 2 equal to cosine theta, which means theta equal to 60 degree, or pi upon 3 if you want in radians. Yep. So this is pi upon 3. Awesome. Yeah, and I think this thing is actually used right. So I think I did this kind of thing when I wanted to prove that FCC is also, the face central cubic packing in solid state, that is also actually like having this hexagonal layer structure. Well, okay, let's not go into that. There's no need for that really. Okay, cool. Next. So that is the solution of this thing. Fine. Trivial products. Okay, you have more problems. Find the angle between the body diagonals of a cube. What do you mean by body diagonals? So how many of these do you have? So you got there to there. It's like 1, 1, 1. Then you might be going from there to there. So it's just 1, 0, 0. And this one is. Wait, that's. Okay, that is in fact just 1, 0. So it's like, okay, that's negative 1, 1, 1. Right? But there's multiple such diagonals. So, huh? Okay, this is along y z only just 0, 1, 1, of course. And then you just do this minus. Yeah, it's just negative 1, 1, 1. And this one is 1, 1, 1. Wow. It's like 1 upon 3 times the dot product, which is just uh 1 as well. It's like, okay, 1 upon 3 equal to cosine theta, theta equal to cosine inverse of 1 upon 3, whatever that value is. They didn't actually give me the thing. Well, whatever. Okay, use the cross product to find. Aren't there like multiple angles because there are like multiple diagonals? So multiple body diagonals, right? How many body diagonals do you have? So, okay, two corners constitute one body diagonal or something like that. So how many such corners? You have 1, you have 2, you have 3, and you have 4. Right, it was like 8 corners, so 4 such pairs, which means you have 4 such body diagonals. And do all of these actually have the same angle between them? I think they do. Yes, they do have the same angle between them. Except if they don't. Okay, well, think. What about these vectors? So going from here to here, and this one going from there to there. Right, that might have a different angle somehow. So that is just 1, 1, 1. And this vector, well, okay, what's this point? This point is 1, 0, 1. So like 1 minus 1, 1, that's that. Oh, it's the same. It's the same. Doesn't matter what you do. Wow. Okay, so all the body angles have the same angle between them. Anyway, next question. See, that's the nice thing about vectors, writing vectors in Cartesian coordinates, because you don't have to visualize. You don't have to actually visualize these diagonals. Instead, you can just, do some calculations, and there you got the angle between them. Fine. Next, you have use the cross product to find the components of the unit vector n hat perpendicular to the plane shown in figure 1.11. Perpendicular plane shown in 1.11. Where is that problem? This is 1.0. You want, so 1.10, that was 1.11. Where is 1.11? There is no figure 1.11 before it. Oh, okay, this is figure 1.11. So you want n hat, which is perpendicular to this thing. Wait, do you even know what these vectors actually are? You don't. So then how am I supposed to do this? Okay, I think they are giving us the information now. So, no, this is not a problem. This is just the introduction to triple products. Seriously, how am I supposed to solve this if I don't even know what these vectors actually are? Do I actually have to do my own naming first? This would be stupid. I mean, we didn't actually solve the problem. We just gave them a method. That's no way of doing it. Huh. Okay, still, how would you actually figure out, what n hat is? Um, what are the things that are given to us, by the way? Maybe we know what's, the length of these segments, and yeah, like having those right, that actually basically tells us the whole thing. Uh, what you could do is just figure out this vector, because now you know what this point is, the position vector. You can figure out this vector, you can figure out that vector, and just take the cross product between these, and reduce it, make a unit vector out of it, and there you go, you got n hat. And of course you have to use the right hand rule, given like, yeah, you want n hat going in this direction and not the opposite direction, right? So that's awesome. Oh, then what you have? You have a scalar triple product. So basically the volume between, right? I'm going to explain this actually. This is something worth explaining. So the way this works is, right, if you want to figure out the volume of parallel pipette with these three vectors as its, sides, then first you need to figure out the area of this base. To do that, you just do C vector cross B vector, but wait, that actually gives you a vector which is perpendicular to this plane, right? Yeah, and then you just have to stack up this area for how much height this parallel pipette has. And what's the height, by the way, is just a cosine theta, or a dot n hat, times this area. N hat times the area is just C vector cross B vector. So is an A dot with that just A vector dotted with C vector cross B vector, or B vector cross C vector, depending on how you want. I think, yeah, B vector cross C vector is better, because then that just gives n hat in this direction and not the opposite direction, right? So then A vector dotted with B vector cross C vector, so basically this thing, right? This would be the volume of this parallel pipette. Nice, isn't it? Uh, right. And this is somehow sometimes written like this thing. It's written like just using this box notation. Throughout my life, I'm actually going to be using this notation, because I know I've been using this notation for a while now, and it is inconvenient. I would like to reserve this notation for a matrix with column vectors as A vector, B vector, C vector. Instead, for the triple product, I will be using, just a determinant, the bars, right? Okay, so, right, A vector dotted will be vector cross C vector. So that thing, you have to do all of the calculation, and then actually you will get the formula for calculating this thing given the components of A, B, C, right? And this is also sometimes written like this. It's written as AXP, AXAY, AZ, then BXBY, BZ, and CXCY, CZ. So this is a determinant. We won't go into detail because that's honestly just a part of linear algebra and not from here. But yeah, that's a determinant. This is the same determinant but in shorter notation, and this is the same thing just in vector form. Okay, so yeah, I guess that should do it. And how do you actually calculate this thing? Well, I won't explain that. Go study linear algebra first and then get back to this. Anyway, yeah, okay. Yeah, whatever, we don't really care about it. Then you got the vector triple product, so A vector cross B vector cross C vector. This thing, it has no geometrical meaning, right? At least no direct geometrical meaning. It has an algebraic meaning. of course, just a series of calculations. Um, right, and it has yeah, it has this formula going on. So okay, how do I explain this? I have a video. I have a whole video proving this formula that A cross B cross C is equal to A dot C, that times of B vector, right? This is a scalar, by the way, so just a scalar times a vector, okay, and then minus A dot B times the C vector, right? Uh, yeah, and also if you have this thing, so like if you have A vector cross B vector and that crossed with C vector, you still do the same thing. You do opposites dotted, as I should say the far away vectors dotted times the middle vector minus the adjacent vector sorted, so b vector dot c vector, that times this thing. And do I really have to prove this? I don't think so. I mean, okay, you can write like this thing, negative c vector that crossed with a vector cross b vector, and you can use the negative to make this b vector cross c vector, right? Sorry, a vector cross a vector, and then this becomes obvious, a vector dot c vector times b vector minus, yeah, you get the thing, right? Okay, so this is not important because yeah, this is definitely just not important. Okay. Uh, right. So this is for babies, of course. Now you know all of this. So I won't be going to that. Okay, prove the, seriously, I mean, I took a whole video to prove that, and now you just want me to prove it directly. How? This is bad, isn't it? So you have to prove this. Uh, okay. I mean, you can definitely do algebra, write down the whole formula for this thing. That's the more stupid way of doing it. So then some other way to prove this? Uh, okay. Well, first of all, we'll just notice some few things about it. Let's think about it. So A vector cross B vector and that crossed with C vector. Or instead, let's go like this. A vector crossed with B vector cross C vector. Right. So let's just think about the plane of B vector and C vector. B vector over here, this thing is C vector. You have the cross product which is along this thing, and that crossed with A vector. Now A vector might be anywhere, we don't actually care where it is. Well, this crossed with this, that's going to be perpendicular to A vector, and also it's okay, this is getting complicated, isn't it? And so it's like perpendicular to our to this vector. So something that is perpendicular to this n hat vector is actually in the plane of B vector and C vector. Surprise? Really? It's not that complicated actually, because it follows this thing. So okay, let's think about it. If something is perpendicular to n hat, then right, how do I explain this? N hat was the vector that was perpendicular to the plane of the vector and C vector, and because of that, because it is like that by definition, what you can say is anything that's perpendicular to n hat must lie in this plane, right? Of course, the converse is much easier to prove. Do I really have to prove this? It's not a math class. So no, just visualize this, that yes, it's actually going to lie on this plane, the v vector cross vector. And by the way, a vector is not in the plane necessarily. So this is hard. This is hard to make you visualize without actually drawing in 3D. But yeah, just have to use your imagination a bit. Okay, so what were we doing? Yeah, right. So since it's something that is in the plane of v vector and c vector, you can actually, if v vector and c vector are not collinear, right? And if they are, this would just be the zero vector, which would mean like, of course, this is going to be true, right? Yeah, like a vector dotted with b vector. Oh, God, this is weird. Right. So if b vector and c vector are actually the same vector, or if they are scalar multiples of each other, then this thing, right? Where did that thing go? Right, this automatically becomes zero, right? Try it out, it will become zero. And if they are not in the same line, then you can write any vector in this plane as a linear combination of these two vectors. Okay, and right, what that actually means is this thing that we're figuring out is also a linear combination of p vector and c vector. So let's just say it's like this. It's p b vector plus q c vector. Now what you can do is take a dot product of this thing with a vector, right, of this whole equation. So what you will get is like a vector dotted with this vector. But guess what? This vector is perpendicular to a vector. So basically the dot product is just 0. So 0 is equal to p times a vector dotted with b vector and plus q times a vector dotted with c vector. And then similarly you can take, oh well, I guess that's all you have to do, huh? Fine. Right, so you can't take a dot with it directly. Well, whatever. I guess this is not a big deal. So, right, you got, how do I even explain this? So basically P and Q have this property that P upon Q, okay, just should write it like that. So just, this goes over here and, right, so P upon Q. Sure, it's going to be this thing, negative of a vector dot c vector upon a vector dot p vector. So you can just, let's just say that p vector is equal to a vector dot c vector times something t, right? T is just some parameter. We don't really care about it. So just some real number. Then what we basically have is this just becomes t, which is some scalar. This times of a vector dot c vector over here, right? That's what t has. And then q will be negative a vector dot b vector times t. So since now t is outside, it's like negative a vector dot b vector and the times of c vector, right? So what we just proved is that this is actually, a multiple of this vector, and it just so happens that t equal to 1. Okay, should I actually prove that? First of all, the magnitude. Think of the magnitude from both of these guys. God, this is hard to. How do you prove that t is equal to 1 all the time? It's not so easy to prove, is it? Okay. But we have to prove that t equal to 1, otherwise that too in a general case. So now what? Let's take a dot product with n hat or something. No, that's gonna kill this whole thing. That's not point. Yes, yeah, that's pointless actually. So let's take a dot product with b vector instead. So this dotted with b vector. Shit, it's not going to work. It's definitely not going to work. Crossed with that, huh? Okay. This is perpendicular to b vector and c vector. Okay, cool. Sorry, perpendicular to b cross c. You can't even take a dot with n hat or something like that. This is stupid. You just have to prove that t equal to 1 all the time, but then that's getting hard, isn't it? Okay, let's just try it out. Let's take a dot product with b vector and see what we get. So this would just be, b vector dotted with this whole thing. So then just b squared over there, and you got b vector dot c vector or something like that. That is stupid. No way. I'm not gonna do that. Definitely not. What about take a dot product with a vector once again? Well, I mean, it's gonna be 0 anyway, right? That's just the way it is. So now what? This is a vector, of course, and this is another vector. And how do I prove that t equal to 1? Okay, you can definitely go with magnitudes and stuff like that, but is that even useful in the end? I don't know. I have no idea. Right, so like square this thing. It's like a squared. Okay, t might be different for different cases. We don't actually know that. So how do I prove that this is really equal to that and then t is actually equal to 1? You can't just take like a coincidence or something like that. At least we have to prove that its magnitude is 1, right? T is equal to plus or minus 1 or something like that. I guess squaring both sides isn't that bad an idea, is it? I don't think so. So then what do you got? It's got like, oh wait. Oh shit, we don't know whether or not this is going to work out. Okay, so since you can't take a dot product with this thing, maybe do something else. Let's take a cross product, right? Yeah, let's take a cross product with something. Let's take a cross product with b vector cross c vector. Okay, so yeah, like n vector. This, let's just call this n vector. So n vector crossed with this complete thing. So this is already perpendicular to n vector, and then n vector crossed with that. That's some vector, right? Oh, this is getting complicated. Yes, it's getting complicated actually. Uh, what do we do now? Or just a vector crossed with this thing or something like that. That's just stupid. This crossed with that. Well, this is already perpendicular to this guy, and this is perpendicular to that guy or something like that. Shit. Okay, this complete thing is already in the plane, so taking cross product is just adding one more thing to it. It doesn't prove anything. That is not going to help. What about just squaring this? I mean, we thought about it. We could square this, right? But then we don't know how it's. Yeah, we can't do anything with it, even if you do square it. Uh, so then what? What about? Oh, this is just so stupid. Fine, that's our n hat vector. You can't take a dot product with n hat vector, and this is not helping. How do you prove t equal to 1? I think that was the step where we had to assume some stuff, right? Or was it? Okay, are there like any hints or something in this? Uh, Wait, are you in component form? That is just stupid. Yeah, that's just stupid. You definitely don't want to be doing that. You don't want to be writing both sides in component form. There must be some better way than that. So, yeah, well, t might be just specific to that particular value, right? Exactly. We don't even know whether or not it's actually going to work. There's some to allow that. Come on, think about it. This is just some vectors, but it's in the plane of B and C. So then if you think about, all right, wait. So maybe, just maybe, this might help. Some other vector that is in that plane, okay, that dot with this thing is gonna make that happen, of course. So, right. Some other vector that is in the plane of the cross vector, of course. Uh, that's like perpendicular of this guy. Okay, that's just stupid because we know this is not going to be 0 in that case. So how can you do it? You can't. Okay. Now what do we do? Do we really have to write in component form? I mean, we already proved this much, but then t equal to 1, you can't prove it directly, unfortunately. You instead have to do this, huh? This, okay, for those particular A, B, C. So we have to do this for a general case, otherwise there's no hope. What if we just do? Well, we did it. We did dot A vector, we did dot n hat, we did dot B vector as well. Nothing seems to be working. Yeah, nothing seems to be working really. Okay. Oh, well, think about it. You could, right. So let's think about A vector in two components. One component is perpendicular to this plane, and one component is along the plane, right? Awesome. Wait, that could be used. So the vector that is right. So the vector, yeah, the component of a vector that is perpendicular to the plane. Well, that doesn't matter. That's going to be cancelled anyway. So might as well just put a vector as something that is in the plane of B and C, right? Exactly, exactly. So then if we do that, okay, let's just say a naught vector is the part that is in the plane. So then this is yeah, like this equation basically turns out to be this thing, right? And now you can take the magnitude on both sides. So what you get is like, oh god, that is awesome. That sure is awesome, right? So now you can take magnitudes on both sides. So what you get is like the magnitude of this guy is definitely just a naught, the magnitude of that times this guy's magnitude b vector cross c vector, and this is equal to t times the magnitude of this guy, which is square root of, you know what, just square that, square both sides. So t square, and then this thing will just become a naught dot c vector squared b squared plus a naught dot b vector squared c squared minus 2 a naught dot b vector a naught dot c vector, and right, uh plus of b vector dot c vector, of course. Okay, cool. So that's awesome. Now can you somehow write this in a way that, you know, like, okay, that's not gonna help. That's definitely not going to help, huh? Since that, oh, this defines like this a not everyone just get off the whole thing. No, that's probably not the way we should be doing it. Now what? So this, yeah, this happens. And does that guarantee that t square equal to 1? Maybe, maybe not. Can you usually write this as a naught squared times b square cross c square? So yeah, b naught, sorry, b vector cross c naught cross c vector, that thing squared. Can you actually write it like that? I don't think you can. Maybe write this in expanded form or something. Oh, okay, okay. This is actually like b square c square sine square theta, which you can change, right? You can change it. You can actually write like this. You can write it as b square c squared minus b vector dot c vector squared. Right, right. Starting to make sense. Just a bit of sense, but still. Uh, yeah. So, hey, think about it. What this thing? Not squared. Wait, wait, wait. And then you can actually split A into two terms, one along B and one along C, right? You can write A, since now it's a thing that is in the plane of B and C, you can write it as a linear combination of B and C, right? And since it has the same power on both sides, you can actually just say it's a unit vector or something like that. So then A square would just become 1. And now think of this thing. Well, now a naught vector, instead of that, you just use a naught hat, right? Exactly. Like a naught hat, just some random vector in that plate, in that plane, that dotted with c vector, that thing square times v. Oh yeah, this is definitely making sense now. Yes, it is actually making sense. Well, still, you got b naught, you got b dot c and that thing squared. That's still weird, but I guess it's okay. Ah, that is very weird actually. So now it's a unit vector and then this dotted with c over there and all that stuff. Okay. First you need b square c squared somehow or something like that. Or you know what? Instead I is using trigonometry. So this would be the same thing as like b square c squared sine squared theta, where theta is the angle between b and c. And this we do not know. Yeah. Right. We don't know about this. Okay. Anything else? You got BC cosine theta over there. You got, once again, A naught dot. Uh, I guess we just, at this point, just break B and C in two terms. Right, that's just a lot of work actually. Should we even do this? So sure, you can break B and C as, you know, components and something like that. I guess, yeah, this is proving that T squared equal to 1 is now much more easier, since you can break B squared and C squared into two components. One along a naught vector and one perpendicular to this thing or something like that. But of course, this thing would just be, oh, it's like a naught vector dotted with c naught vector. And b square is like b naught squared plus, this is called the other thing as b dash squared. Right, right. And then this thing, what was I going to do? Oh yeah, so once again, just instead of that, just put b squared and c. Right, just put those things. Uh, this is going to be hard. Fine, but it can be done. It's not that bad actually. So what you can prove is like t squared equal to 1 or something like that, and from there you can get t equal to 1 or negative 1. But since you think about the direction, right, it will basically be 1 all the time. So there we go, just prove this thing. This was hard to prove without proper experience. This is actually hard to prove. Fine, so that's done without writing in component form. Okay, next we have to prove that this is equal to 0. So you got a cross b cross c plus b cross c cross a plus c cross a cross b. Okay, and under what conditions does this happen? Fine. It's gonna be hard. This question, under what condition a cross b cross c is equal to a cross b cross c? This is in the BC plane, this is in the AB plane. So what must happen is that ABC all must be in the same plane. And then you can have this thing happening. Right. There might be more conditions, but well, whatever. So of course ABC must be coplanar. Then B cross C is just the unit vector which is going upward or something like that. Okay. Right, of course. And then so it has like BC, but that times of cosine, okay, that angle between them, right? So magnitude wise, what will basically happen is like, okay, so magnitude wise, A times the magnitude of B cross C, that's equal to magnitude of A cross B times C, right? What it means is like B hat crossed with C hat, right? The magnitude of that is, okay, that is sine theta. The sine of the angle between B and C, that's equal to sine of the angle between A and B. That looks interesting. Wait. The common thing is B, right? So you got B vector over here. So the angle between, and of course I don't want the magnitude, so it could be either clockwise or anti-clockwise, both will work. So yeah, the sine of these guys, right? These angles must be the same. So B vector must be the angle bisector of A vector and C vector. Basically, that's what this is saying. Okay, okay, awesome. Right. And yeah, then this does happen. Actually, only the magnitude case this actually happens. Right, so B vector is in fact angle bisector of A vector and C vector. You know what, first of all, just write everything using unit vectors. So then you can just write, yeah, again, scale up our B hat such that it just becomes like A vector plus C vector or A vector minus C vector or something like that. I guess you can do that. But either A and C must be the same. Wait, what? So if A and C are the same, then this happens. Okay, sure. Well then, okay, that's pretty obvious. If A and C are the same, then this does happen. Or you should just have that, yeah, it's just the angle bisector of these guys, which would mean, uh, you know, you could replace B vector by A hat plus C hat. I know there's some scaling to be done, but whatever. So just A hat plus C hat. So what you basically get is like A hat crossed with A hat plus C hat, and that crossed with C hat. This is equal to A hat crossed with A hat plus C hat, and that crossed with C hat. Well, of course, this cancels because, right, distributively, and this cancels. Oh, okay, that's like A hat crossed with A hat cross C hat. That's equal to A hat crossed with C hat, and that crossed with C hat. I guess we should just do this thing this time. That is like, okay, A hat dot C hat. Well, that times of A hat, then minus, well, these two combined is A squared. Oh, that's one unit vectors, right? Oh, just C hat over there. This is equal to, so once again, this and that, which would be A hat dot C hat. Well, that times of C hat minus, oh, it's the same thing. It's the same thing once again, right? C squared is 1, so it's just A hat over there. Okay, slightly different. Fine. So what you get is like A hat minus C hat. Wait, what? Something's not going correct about this. Am I like sure this is the thing? It must be, right? It must be. It's just the addition of these two guys. Yeah, but that should be the case. Okay, whatever. Like, okay, A hat minus C hat. Uh, and over here we're going to, yeah, over here too you're going to get the same thing. So what you get is like A vector, sorry, A hat dot C hat minus 1, that's equal to 0. So if A hat and C hat are the same thing, right? Then what that would mean is like B hat is also just the same thing. So all these are the same vector or the same directions at least. That would be one thing. But we already considered the case when A and C are in the same direction. So no need for that once again. And then what if A hat and C hat are not the same? Then this must be 0, which would mean that A vector dot C vector equal to 1. Oh wait, A hat dot C hat equal to 1, which means these must be the same direction once again. Oh, right. There's only one way, huh? That these must be the same direction. So A and C must be the same vectors. Otherwise, this does not actually happen. Wow, that was something. Okay. Position, displacement, and separation vectors. The location of a point in 3 dimensions. Okay, I mean, okay, that we already know about. Yeah, we all know that. This is funny how this went from electrodynamics to mathematics real soon now. Okay, so some notation. So the source point R dash and field point R. And what's this small letter r? So this is the subtraction. Fine. So from the source to the point, the vector going from there to there. Okay. Of course. Uh, well, yeah, whatever. Find the separation of vector r from source. Oh, come on. Are you serious? I won't be doing that. Okay, let's do it in my head. So this is source point. This is the field point going from there to there. It's like 2, negative 2, 1. That's our vector. And you want what? Okay, so you want to find its magnitude and construct the unit vector r hat. Are you serious? What's the magnitude? It's the square root of 4 plus 4 plus 1, which is 9, right? Yeah, so 3, which means our unit vector will just be 2, negative 2, 1 upon 3. There you go. Next, how vectors transform? Okay. What is all of this? Oh, okay. Well, linear algebra, huh? So this is a rotation matrix. Okay, they already told us it's a rotation matrix. Fine. And now you want rotation matrix in 3 dimensions. That's some weird thing. Rotation matrix in 3 dimensions. Okay, this is new. I didn't think of it yet, but yeah, like you could have rotation matrices in 3 dimensions. I've only been dealing with 2 dimensional rotation matrices till now, which are complex numbers basically, right? But for a 3 dimension case, what could we do? There is a way. I think I know a way how to do it. So say you want to rotate a vector, a vector. You want to rotate this along, sorry, about a vector n hat and by angle theta. Uh, right. So first we'll just have to decompose this vector into a vector that is perpendicular to n hat and along n hat. Right? These two kind of vectors. So the way I'll do, first of all, the vector that is perpendicular, sorry, that is along n hat. Right. That would just be this thing, a vector dot n hat, and that uh, times n hat. That's this vector. Okay, then you want to subtract this from it, so that what you basically get is just, the vector that is, uh, perpendicular to n hat. And then you want to rotate this component only by theta. So the way to, rotate some vector x which is perpendicular to n hat by theta along n hat using the right hand rule would be to do this thing. You just do n hat cross uh, cross x vector and sine theta and x vector cosine theta. So yeah, like think about it. If this was the complex plane, x vector was in complex plane and n hat was just the plane perpendicular to this guy, right, going outside, then taking cross product with x vector would be like multiplying by iota. So this actually what it's doing is like it's just doing, cosine theta plus I sine theta that applied on x hat. Or on x vector. Basically, that's what it's doing. It's just doing multiplication of complex numbers, right? So rotation in 2 dimensions. But yeah, but in vector form, right? So once you do this thing on this vector, so like this is equal to our x vector. Once you do this on this, right, this vector that you get is the vector that is rotating, or that's rotated by theta from x vector about n hat. Yeah, right. And now add to this the component along n hat, and there you go, you got the thing. Awesome. So how do I actually explain? Right, you could think of matrix notation. So cosine theta plus sine theta times the n hat cross matrix. I know you guys don't know what this is. For now, I'm just gonna, write down the thing and then I'll explain everything. So this matrix, and of course it's because cosine theta times the identity matrix because it's just the same vector once again. Okay, well this applied on our x hat, on our x vector, which is just this vector, right? And you know what? This seems familiar. This seems like this. Okay, so it's like just n hat cross a vector cross, so a hat, a vector cross n hat, right? So this matrix applied on this vector, I bet that is the thing, right? Exactly. So this applied on this vector, that's our new rotated vector, and to this you add this thing. To this just add uh, a vector dot n hat, right? So yeah, this should bring it. Now of course a vector cross and hat, you can add like negative n hat cross this thing. So then you can use more matrix notations. It's like cosine theta times identity matrix plus sine theta, the n hat cross matrix. Well, okay, this is a matrix. Then you apply, apply this on top of another matrix or two matrices. In fact, it's like this thing n hat cross. So this matrix, and then once again n hat cross. And this applied on a vector, or you know what, actually, yeah, just negative of all of this, just negative of all of this. So I'm gonna squeeze this, right? So yeah, that's what I'm talking about. Okay, and then but this thing once again, a vector dot with, oh, this is so complicated. uh right. You can think of a column vector as a matrix. This is stupid, but whatever. So plus n hat, this matrix, quote unquote. It's not, it's actually just a vector. And then you have this thing. So this is a transpose of our column vector. What this basically is just a dot product. So like this applied on some vector. So if I have like a vector transpose applied on a vector x vector, what it does is like it's just this thing ax. Okay, I should say b vector because I'm using x, y, z later on. So ax, ay, az, and then this applied on this column vector. So every vector, quote unquote, is just a column vector in linear algebra. So yeah, what it basically is just this thing, which, yes, it's just a dot product, of course, because that's the way this is calculated. It's just a vector dot into b vector. And of course, this would be the column vector. So yeah, right. So and once again, this you can think of it as just the, you know, how do I even explain this? Uh, the column vector, of course. Okay. Okay, cool. Right. So can you actually, okay, let's think about it. If you have a column vector 1, 2, 3, and you're multiplying this with uh with a row vector, right? So not the usual way that you do to take the dot product, but instead you're doing this so that, you know, you think of it like as a matrix or something, right? If you can think of it as a matrix, so you know, doing this thing. Once again, how do you actually do this? First of all, you do this like one that goes into this, so you just get like 1, 2, 3. Then 2 goes into this matrix, right? Yeah. So this matrix applied on 2, which would just be 2, 4, 6, and then this matrix applied on 3, which would just be 3, 6, 9. And right, so you know, like if you have something like this x, y, z, you're applying it on that. So what would happen is like, first you just have x going to this thing, right? So this matrix being applied on that, so it basically converts your x I hat to just x, right? So everything will be individual. First of all, you just gonna take x first, then y, then z, and then combine the effects together. So the first thing basically becomes this, right? Just one. This is hard to explain. Just x basically, and then y just becomes 2y, z just becomes 3z, right? So y hat, if you pass that as an input in this complete function, right, this matrix, then in the first part your y hat just becomes 2y, and that is multiplied with this vector, right? That's what this matrix is doing. And in reality, what this matrix actually is this thing. So yeah, I mean, this is very legitimate. You can think of this as a matrix. Don't get scared. Don't think that this is like just vectors written in a more complicated form. No, it's actually a matrix. I know, very simple one, maybe even redundant, but still it's actually a matrix. So you can write that as a matrix, and then you can apply this on x, y, z, right? Whatever vector you want to pass in. So what that means is like, you know, you can think of this as a matrix, right? And then yeah, just add these two matrices. So this is a matrix, this is a matrix. Add these two matrices up, and then apply all of that on our vector, which is just a vector. There you go. So this is our rotation matrix. It rotates by theta about the vector n hat, and this works for any kind of a vector really. So yeah, this matrix is the rotation matrix. So yeah, still hard to do it directly though. Well, whatever. So now you know how like rotation would work if you don't construct a rotation matrix, right? And you want to just do it directly, then there is a way to do it. So it's not that complicated. But yeah, why not just, you know, first of all calculate the whole matrix and then, you know, apply it on any vector that you want to. Better, right? Definitely better. So that explains this thing. There's all this trigonometry going on. What are they doing? Oh, so they're like rotating about x vector and y vector and stuff like that. Okay. Oh, okay. So they're rotating related to the axis that they gave to us. This is so stupid. Why would you want to do that? Why not just, you know, rotate about some random vector using this thing? Yeah, that is so much better, isn't it? Okay, whatever. Oh, and I didn't actually explain what this n hat cross thing is. So you can think of a cross product as a matrix as well. So, you know, write down what, well, let me just show you. So, let's just say f vector is this thing, fx, fy, fz, right? It's not a function, it's just a vector, it's just f vector. And you do f vector crossed with x vector. So x vector is just this vector, x, y, z. Right, so just do this crossed with x vector. Once you do all of it, what you're going to get is something like this. You just get, you know, zfy, then minus yfz plus something x, 0x, right? So the first thing is just a linear combination of xyz, and then similarly the other thing is just a linear combination of xyz. This is also a linear combination of xyz. So it's as if you applied a linear transformation on the xyz to get another vector. Think of it as an input. Think of this thing, this complete operation as a matrix as a matrix. You're applying this matrix to this vector to get another vector. So that's why you can think of this as a matrix, right? And I won't go to details on how to actually write this, just giving you idea. And they are not doing that anyway, so we didn't actually have to do all of it. Anyway, right, so, okay, differential calculus, this we'll do later. First, let's just do these problems. Prove that two non-dimensional rotation matrix preserve dot product, that is, show that A y by plus az bz is equal to ay by plus az bz. Wait, these are vectors or what? Or are these matrices? No, sorry. The two-dimensional rotation matrix 1.29 preserves rotation. Oh, okay. So these are the vectors after you apply the matrix to it. Are you serious? It just rotates. It doesn't change the angle. So there's nothing to prove really. It's already true. Huh. Why would you think that it changes the dot product? It does not. It doesn't change the angle. Geometrically, it doesn't. It just rotates. So, yeah, it doesn't, right? I mean, just think about any two random vectors and think of, consecutive operations. So, first operation is like you're rotating about this particular axis. Is the angle between these vectors will not change because the whole 3D space is being rotated. So this is also rotated by the same angle about this that this thing is. Then rotated by some other axis. Once again, this angle between these two vectors is not changing, and then you rotate by some other axis, angle not changing. The lengths of these vectors are still the same. So the dot product, which is AB cosine theta, by definition, well, that doesn't change. So yeah, first one just done by words without actually calculating anything. Okay. Next question, please. What constraints must the elements of three-dimensional rotation matrix satisfy in order to preserve the length of A for all vectors A? Right. So I think, wait. This is kind of weird. The determinant must be 1, right? Since it does not change the angle between two vectors. So it also does not change the volume of a certain space when it's doing the transformation. Exactly. So the determinant must be 1. But still that does not actually guarantee that this is going to work, right? But yeah, that's like one condition. There might be more conditions. You know what? All we actually have to do is just match it with this thing. So this matrix, right? Just match it with that and then see what restrictions we can put on it. And I won't I won't do this because it's just so complicated. Why should I do it? Okay, figure 1.9. Sorry, problem 1.9. Find the transformation matrix R that describes the rotation by 120 degree about next. Right. So the point is clockwise as you look down the axis. So our n hat is just 111 upon square root of 3. And now just do this thing. And our theta is 120 degrees. So, right, let's start doing it. First of all, we need to figure out what n hat cross will be. Right. So first of all, actually, I guess I really need to show you what f cross would be as a matrix. So yeah, f vector is equal to fx, fy, fz. Right, and well, f vector cross x vector, that is equal to 0x vector. So just have x, y, z over here. Oh, not x, but just x over here. Okay, so this cross with x vector. This is our x vector. Okay, so 0x, then plus fy z. Okay, we don't want it. We want what's with y. Minus fzy, then plus fyz. Okay, then for the y component, just 0y over there. Then what was I going to do? Oh yeah, this thing. So just fzx plus 0y and then minus fxz. And for the third component, we'll just 0z over there. And then is fxy and minus fy. Is that correct? Yes, it's correct. Minus fyx. So as a matrix, what f vector cross is actually doing is just this thing: 0, negative fz, fy, fz, 0, negative fx, negative fy, fx, and 0, right? And now what we have to do is just calculate it by using n hat cross, and yeah, hopefully it's gonna do the thing. Right. But I actually don't want this to be n hat. I still just wants to be n vector, but like doesn't matter, right? Because look, you got this, and okay, I think it does matter. So in this particular case, you have to use n hat cross, and over here you can use n cross as well. So yeah, like over here as well, you can just use n vector itself and not n hat. Yeah, I guess that makes sense. So yeah, like just completely change this. It's just n vector cross and then n vector cross. Okay, and then this thing is just n vector and then n vector transpose the matrix multiplication of these two guys. Right. This should be doing it, right? Exactly. Okay, so now let's do the thing. So our n vector cross, what will that thing be? It's just God, this is so weird though. Yeah, it's just well, first of all, just need 0, 0, 0 in the diagonal. Then you need negative fz. So what's the z component? Was just 1. So just negative 1. Then you got 1, 1, 1, negative 1, and 1. Well, yeah, that's our n vector cross, of course. So this is the matrix. Okay, what's the matrix applied on itself? First of all, that's one thing you need to figure out. This is just so weird. Uh, yeah, this is very weird actually. Well, whatever. Let's see what happens. So this applied on itself, right? Okay, so just 0, negative 1, 1, 1, 0, 1, negative 1, 1, 0. This applied on 0, negative 1, 1, 1, 0, 1, negative 1, 1, 0. I hope it's correct though. Hopefully. Oh god. This is just so stupid. Like this, all of this you just have to calculate. Why can't you just use a computer for this thing, right? Okay, whatever. So what do you get? The first vector goes into this thing. You just well, that's 0. Okay, you got one of this minus one of that. Just got negative 2, then negative 1, and just 1. Yeah. What about this one? That goes over here. Just negative 1 of this guy. That's not there. This is just 1. So 1. Then that's negative 1 plus 1 is just 0. Then that's 1 plus 0 is just 1. Okay. Wow. And what about this one? Just add these two up. Yeah. So that's going to be what? It's still like you got negative 1, negative 1. Shouldn't there be a negative 1 over here as well? Well, yeah. There should be a negative 1. Why is that not there? For the second one, what do? You just do. Oh shit. Okay, so like the y thing does not matter, but then the z component is in positive, the x component is in negative. Exactly. It's like it's supposed to be negative 1. Right. That's what it's supposed to be. Like this. Exactly. So this first vector is just wrong. In fact, all the vectors are wrong. So this goes over there, just negative 1, negative 1. Okay, cool. That's just 0. This thing is negative 1. And this thing is also negative 1. What about this one? This goes over here. That's a 0. Right? You got negative 1 of this guy, which is just 0, 1, 1. And that plus this guy, which is just 1, 2, 1. Wow. Awesome, isn't it? Oh, it's getting complicated. Okay, I think something must happen. wrong? What is that actually? Am I doing am I actually doing it correctly? I have doubts now. No, the x is not. Oh shit. Oh shit. Okay, the right. It's supposed to be fz. It's supposed to be positive fz over here, and this is supposed to be negative fx. Ah, okay, that is negative one now. So it's actually like this, right? So there was a bit of problem now. Okay, this is good. Now we can actually do this. One negative one over here. Let's do the thing. Seriously, just figuring out this thing is just so complicated, isn't it? Okay. So what do you get? Uh, one negative one just okay, negative one, negative one just negative two. Then plus one, this thing is just plus one as well. What about this one? So just one over there. Negative two. Okay, it's one. Cool. What about this one? Uh, right, just one over here. Then you got one over here. And that's negative one, negative one, just negative two. Oh yeah, this looks much more symmetric, of course. Awesome. So that's this thing, right? Uh, yeah. Let's write that down. So n vector cross, and then that applied on n vector cross. That's equal to this. Okay. Now let's figure out what this matrix should be. So what's cosine theta? Well, it's 120 degrees. It's just supposed to be, you know, negative 1 upon 2 over this. Okay, cool. So it's just negative 1 upon 2 identity matrix, and then sine theta is square root 3 upon 2, but then this actually has 1 upon square root 3 because the length of the vectors is just 1 upon square root of 3, of course. Sorry, it's just square root of 3, so 1 upon that, so that you actually get an n hat. So it should be like 1 upon square root 3 and then n vector cross. Right, so just square root 3 upon 2 times 1 upon square root 3, that's just 1 upon 2. So 1 upon 2 n vector cross. Awesome. So just this thing, it's complete thing, negative of that actually. So 1 upon 2 out, it's just the identity matrix minus minus this vector. So that applied on this, right? We just have to figure out what this thing is actually. So what is identity matrix minus this vector? Is just 1, 2. Oh shit, that should be 0. Okay, it's just 1 over there. It's negative 1. Well, that's just 1. That's just 1 as well. Is 1. This thing is 1. Wow. Negative 1, 1, negative 1. Yep, that's what this thing will be. Now you want to take another multiplication. So this applied on, is that correct? Once again, that's just negative 1, 1 over there. That's negative 1. This thing is negative 1, 1. Yeah, that's right. And this applied on this guy. Negative 2, 1, 1, 1, negative 2, 1, 1, 1, negative 2. Okay. Oh, actually, I should probably write this down. So copy paste. Just resize this. Okay. Yep, that's supposed to be half and everything, but we won't do that. Not yet. Okay, cool. So now we actually want to calculate this thing first. Wow, so much complication. Let's do it. The first one goes over there, just negative 2 plus 1 minus 1 is just us like that, so we put over there. And this one, right, just 1, negative 2, and then negative 1, which is negative 2 as well. What about this one? Just 2. 2 plus 2 is just 4. Okay, interesting. Then this, okay, right. 2 plus 1 just 4. I think it's another symmetric stuff. Okay, it's just negative 1, negative 2, plus 1 is negative 2, of course. This one would be, once again, just negative 2. And you can guess the next one, of course. Yeah. It's just negative 2 over there, and this one is 4. This one is negative 2. So then 1 upon 2 of this guy, I'm going to put that 1 upon 2 anyway. You know what? Yeah, who cares? So this part, this complete part, what that actually is just 1 upon 2 of this, of course, which would just be just this thing. Negative 1, 2, negative 1, negative 1, negative 1, 2, 2, and yeah, this. Okay, so this thing, and then you want plus this, right? Exactly. Let's try it out, of course. So yeah, right. What was the thing? Okay, the column vectors is repeated, but that with the coordinates multiplied. Yeah, of course. So our n vector is just 1, 1, 1, which means oh, this is just that. It's just 1, 1, 1, 1, 1, 1, and 1, 1, 1. Yeah, that's what this thing is. So you just have to add these up. What do you get? You just get 0, 0, 3, 3, 0, 0, 0, 3, 0. Right? Yeah. So this applied on A. Oh, oh, that's it, huh? I'm stupid. God, no. Oh, this was easy, isn't it? I should have just seen what happens to the unit vectors, and that would give me the thing. Okay. Of course, this is not having that, the unit vector thing, right? So actually, what you gotta do is divide by n squared. So in this case, n squared just be 3. So 1 upon 3 of this guy. Guess what? It's just this thing 0, 0, 1, oh, oops, 0, 1, 0. I think 0, 0, 1, 0, 0, 0, 1, and then 1, 0, 0. And that about A vector. So yeah, that is our rotation matrix. Easy as that. I guess all of this could have been prevented if we just went with the most easier method. Like, okay, just figure out what happens to the basis vectors and then just construct the matrix like that. So what happens to this vector, what do we call it, the x hat vector? What happens to that? One is like a polydiagonal or something like that. We're rotating by how much though? By 120. Okay, that's a weird angle. How would I know what's going to happen if, huh, interesting. 120-degree, huh? Try to imagine it. We got a box, right? Okay, quite like that. So then this is the body diagonal. This is our x vector. Rotate by 120-degree about this. How? Uh, and then this just somehow becomes this. No, can't be, right? Or is that the thing? Uh, like if you will look on it from the top or something, and then something. Okay, okay. I think I'm starting to understand what's going on. The angle between the angle between the projections of this thing on, okay, on the plane perpendicular to this vector, but those actually have 120-degree between them because this is symmetric to all of these vectors on the basis, right? All of these basis vectors. It's just yeah, it's symmetric to these. It's equidistant from all of these guys, which means that if you take the projections of these basis vectors onto the plane which is perpendicular to this middle vector, you'll just get it. You just get this thing. You'll just get this 120 angle between each of these projections. Right. Okay, that explains it. So when you actually rotate this by 120-degree, you are indeed getting this. You are actually getting, or you're getting this actually. So since right hand rule, it's going to be rotated like this. So you'll be getting this thing. You'll be getting uh, y hat. So rotate x hat, you'll just get y hat. Rotate y hat, you will get z hat, and so on. So this is no surprise that the matrix we got was just converting your x coordinate to your y coordinate and your y coordinate to your z coordinate. Yeah. Wow. Just wow, of course. This was very unexpected. Right. Yeah, that's the thing, of course. So you are indeed doing that. Okay. So all the work that we did, you could have just prevented that by thinking of what happens to the basis vectors. You know what? From now on, I'm just going to do that. Figure out what happens to the basis vectors and scrap all the method. Okay. Huh? Oh, okay. They're also giving in what sense you're rotating. Rotation is clockwise as you look down the axis towards the origin. Down the axis. So you mean when you look from here? Okay, so this is my eye looking like that. Then this should be clockwise. So it should be going like this. Ah, okay, then you are actually right. The inverse of this, right? So your z will become y, your y will become x, and x will become z. So the vector, so the matrix you're actually looking for is just this thing 0, 0, 1. So x becomes z, right? Our x hat just becomes z hat now. Our y should become uh, x hat, so just 1, 0, 0, and 0, 1, 0. This is the rotation matrix we're actually looking for. But yeah, a more rigorous path would be just, to calculate the thing using the formula I actually gave you. Right. Uh, awesome. I mean, if it was like some weird angle, not 120 degrees, something else, then you would just plug the formula into a computer, calculate it. Yeah, I mean, let the computer calculate it, of course. And yeah, you got your matrix. So, right. Problem 1.10. How do the components of a vector transform the transformation of the coordinates x bar, I think the transform x vector, okay, equal to x, y bar equal to y minus a, z bar equal to z. Y minus a, are you serious? Wait, why is this minus a? Oh, it's just translation. Okay, it's not a linear transformation, it's just translation. Right, of course. Uh, are the components of a vector transform under the translation of coordinates? Wait, I don't understand this. You already gave me how the components transform because look at this. So what component are you talking about? What do you want me to describe? It's just a translation. Yeah. So now what? Uh, for random vector, of course. Wait a second. Oh, okay. I see what's right. So it's not that the vector itself is transforming the points that the vector right has as its endpoints. Those 2 points are transforming according to this translation, and what that would mean is, yeah, the vector does not change. It's just translation in the end. It's not rotation. Rotation would change the vector, of course, but that's not the thing. So yeah, it's not going to change. Okay, B is how do the components of vector transform under the inversion of coordinates? Okay, so x dash is equal to negative x. Okay. So the thing is, this is actually linear transformation. So linear transformations are not just applied on points or on position vectors. They can also be applied to displacement vectors, and you will still get what happens to the vectors because linear. I mean, they are linear. So m vector, sorry, m the matrix, m matrix on a vector minus m on a b vector, that's the same thing as the matrix applied on a vector minus b vector. So this displacement vector is transformed, right? It's transformed by applying the matrix m on it, and it's the displacement vector between the new transform points as well, right? Because it's distributive, right? This matrix is actually distributive, which means, yeah, just figure out displacement vector and then apply this matrix on the displacement vector. There you go, you got the transformation. So how do the components of the vector transform? Well, they just become opposite. So yeah, those are also just going through inversion. No big deal. Okay. How does the cross product of two vectors transform under inversion? The cross product of two vectors is huh? It's properly called a pseudo vector because of its anomalous behavior. What? I don't get it. What do you mean by that? Anomalous behavior. The cross product of two vectors is properly called a pseudo vector. I don't understand this. Wait, what do you mean? A cross product is not a pseudo vector. It's a vector itself. So why would you say this? What anomalous behavior? Wait, is there some section which gives me? Wait, there's nothing, huh? You won't tell me what kind of properties it has that made you call this a pseudo vector. Whatever. So how does the cross product of two vectors transform under inversion? Uh, okay, well, matrix multiplication is, yeah, so applying a matrix is not distributive over cross products, I think. Yeah, it's definitely not. So let's think about it. Suppose initially the cross product was a C vector equal to A vector cross B vector, and now after applying the matrix, what you get is like C uh, dash vector that's equal to the matrix applied on A vector. Okay, and this crossed with the matrix applied on B vector. Uh, Weird. How do I even express this using C vector? I don't know. Matrix applied on B vector. Yeah, I definitely do not know. Matrix applied on A vector though. You could think of A cross as a matrix, but then the matrix applied on A cross is a different story altogether. So this is definitely not the same as that. Okay, under inversion, what's actually happening is that it's just negative of that. So, under inversion, nothing much happens. It's still the same thing. So, like C dash vector is actually equal to C vector in the end. So the cross product does not change. Fine, but that's only for inversion, not for any such random transformation. Yeah, I mean it's just coincidence. It's not something that's going to happen all the time. Okay, cool. Then D is how does a scalar triple product of three vectors transform under inversion? Such an object is called pseudoscalar. So the okay under inversion, well the determinant of this thing is -1. So the scalar triple product, well yeah, it just becomes negative of what it was. Easy as that, really. The volume does not change because it's the magnitude of the determinant. Right, determinant can be positive or negative. That's why. And yeah, so the volume does not change, but the orientation changed. So using the right hand rule, it's now opposite of what it should be. So it's negative, right? So yeah, so such an object is called a pseudo-scalar. What? I don't understand this. Oh, okay. I think I get what you're talking about. So right. Okay, so things that can involve negative numbers as well, right? So the determinant is actually a pseudo-scalar because it's not. Oh, wait, but scalars can be negative. So what distinguishes it from a pseudoscalar? Because the negative sign is used for direction, orientation. It's not used for actual geometrical, like physical properties of the thing. No, it's used for orientation. So maybe that's why pseudoscalar. Anyway, next section is differential calculus, which we'll do in the next video. This has some notation that is worth understanding. So, like the del operator, divergence, curl, gradient, all nice stuff. All right then. So we'll stop here. I'll see you guys in the next video.